Where are we at? Okay, Zoom's telling me I'm having some audio issues. This may be coming from a few sources, so give me just 1 second to make sure I've got things working. I may not be fully recorded. Okay, we will see. So a few things. First, I hope you guys had a lovely weekend, a happy holiday, and all of that. Second, you may need to turn me up a little bit today. I might be a little bit quiet. I contracted some nasty upper respiratory infection last Thursday, Friday, something like that. So I'm getting better, but still not quite all the way there, and I don't have my usual volume. Those who know me know I'm generally fairly soft-spoken already, so I apologize if I'm hard to hear and crank the volume a little bit. I'll try to make sure there aren't any sudden loud noises in the background that blow your ears off if you're using headphones or anything like that. I want to talk today about first order linear equations. We're going to see the kind of full story. I introduced the concept of what we're going to use to solve them last Thursday. And I want to kind of go through the argument with you and show you the procedure. I'm curious, did anybody attempt to solve any of the first order linear equations using the integrating factor method that I mentioned at the end of class on Thursday? You can use the hand raise or hold spacebar to talk as always. It's okay if you did. That's all right. Okay. Let me flip on the dot cam. We can talk a little bit more. Didn't have that up, did I? Okay. The other thing, of course, we need to talk about is the exam. I've been having some second thoughts about the exam date, and it's going to kind of depend on how quickly we move through some of the material. I would like for us, it's not you, this is you. I would like for us to get through exact equations and solutions by substitution before exam 1, because it just kind of fits neatly to have exam 1 cover chapters 1 and 2. When we move into chapters 3 and 4, things are going to get a little bit different. This section can be a little tricky. This section is quite easy. And the others we've actually already covered, with the exception of 2-3, which we're going to finish up today. Direction fields is not a whole lot more to do than what we've already done. So today we're going to talk about first order linear equations. We might talk about exact equations. There's probably going to be time. I don't know if there's going to be time to get into 2.5 today. I probably expect that there will not be time to get into 2.5 today, which I'm going to have to cover that tomorrow and then test you on it on Thursday. So remind me before we go to do a little poll. We can kind of feel that out, because I know we lost a day this week, and I don't want you guys to feel any more rushed than is necessary with this very short course. But right now, the tentative plan is still as it was left last week, to have exam 1 be this week, Thursday probably, subject to some possible changes based on a discussion later today in the class. But before we do any of that, we have some more mathematics to talk about, so let's do that. Okay. Sorry, forgive me. Of course, it's MAP2302 differential equations. Today is it's the 7th, right? 6th? 6th. July 6th, I believe. Yeah. Okay. What are we doing today? Today, we're going to talk about first order linear equations. And how to solve them. We're going to learn how to solve every single first order linear equation, which is pretty badass. There are not a whole lot of like kind of families of differential equations. We're like, fuck yeah, I can always do it. Here's one, right? Here's one where we can always do it, which is great. I think this is section 2.3 in your textbook. And your book's treatment of the content here is not bad at all. I encourage you to go ahead and read the textbook on this section. It's good. That's not always going to be true, but it is true of this section. We're also going to talk about exact equations. And this is section 2.4. Those of you who have taken Calc 3 may have a little bit of an easier time kind of contextualizing the exact equations. These are kind of differential equations, which when written in differential form can be seen as the total derivative or exterior derivative, or you can call it exact differential of a function. And then the other thing I want to do is set a firm date. For exam 1. Because we haven't quite done that. I think we talked about it a little bit last Thursday, but I want to make sure it's concrete, fair, we're all comfy with it. So there'll be some voting involved down here. Make sure you stick around, participate. Please don't tune out. Okay. Section 2.3. First order equations. One of the difficult things in this class, from my perspective, is kind of choosing how much theory to give you guys. I know it's possible to get quite lost in the theory, and when it comes to differential equations, this is one of those places where you can kind of get your feet wet without having any idea of the underlying theoretical constructs. And then for the purposes of engineering and physics, that's great. That's really all you need. You just need to know how to solve the equations. But I want to talk a tiny bit about theory here. I've mentioned why we call linear equations linear. Actually, it's not super important here, is it? Maybe I'll save that till when I talk about general linear equations. Let me just go ahead and remind you definition. First order linear ODE is one which can be written in what's called standard form as you can write it using the Leibniz notation or the prime notation. I like the prime notation, but your book uses the Leibniz notation, so I'll write it like that first. dy dx plus p of x times y is equal to g of x. Which in prime notation is y prime plus p of x times y equals g of x. The term linear I've mentioned a few times in this class, and it is important. Of course, it's the equation is called linear because as functions of y prime and y, right? As a function of y prime and y, the left-hand side is linear. And what that means is that if you were to plug in a linear combination of functions for y, if you were to plug in y equals a times f of x plus b times some other function h of x, then this equation could be split up into two equations. Each one's looking exactly the same. That's kind of what linear really means. It's going to be really important when we talk about higher order linear equations, the fact that you can kind of superimpose solutions. If you have two solutions and you add them together, you get another solution. That's called taking a linear combination. Or if you multiply one solution by a constant, add it to another solution times some constant, then that will give you another solution of the ODE. And that's the sense in which we care about linearity. And it turns out that linear differential equations come from things called linear differential operators. Linear differential operators are the knees of the B. When you really want to understand what's going on underneath a differential equation, the goal is to actually understand the operator that that yields the equation. But our textbook doesn't really take the operator approach ever. So we're going to kind of suppress that way of thinking, at least until we get to chapter 4. I told you that the trick to solving an equation like this is to multiply through by some special function called the integrating factor, and then interpreting the left-hand side a certain way. So I'm going to go ahead and show you that interpretation. I'll remind you what the integrating factor is. I'll show you how we interpret that left-hand side and just give you the nuts and bolts of how to solve an equation like this. But a quick comment before I do that. If using the methods of this section to solve an equation, differential equation, you must first put it in standard form. And the kind of vocabulary here in differential equations is unfortunate. We've called a few things like standard forms, normal forms, differential forms. We've got all these different kind of names for ways of writing what are essentially the same thing. But here, when we're talking about first order linear equations, this is what we mean by standard form. So in order to apply the methods of this section, the whole integrating factor thing, you need to first rewrite your equation like this. And in other words, you need to make the coefficient of y primed equal to 1. You need to pull all the y terms to the left-hand side and collect them together. And then the right-hand side needs to have no y's at all, just a function of x, or a constant or nothing, the right-hand side. Just when we write g of x there, what we mean is that there's no y's. So you got to have y prime plus something times y. So you got to put all the y's together and factor them out. And that thing that's left over will be your p of x. And then your right-hand side, no y's at all, no y's or y primes. If you don't write it like this, you get into trouble. Okay. Last time we said the trick to solving one ODE in the form of equation 1 up there is to multiply through by the integrating factor. Which is the function mu of x. This is the lowercase Greek letter mu. It's the sound in Greek. It's the lowercase mu of x, which is e raised to the power of the integral of p of x dx. Or if you want, you can say, you take any antiderivative for the function p, shove it in the exponent of e. That's the thing through which you need to multiply this equation in order to solve the ODE. Multiplying through by that doesn't give you the solution right away. But what it does do is it gives you an expression on the left-hand side that you can then reinterpret using the product rule. And once you've done that, you'll be able to solve the differential equation basically by separating variables, by integrating on both sides. Why? Well, here's a very short proof. If I multiply through if I multiply through equation 1 by the expression mu, we get e raised to the integral of p of x dx times, I'm going to use the prime notation, y prime plus p of x times y equals e raised to the integral of p of x dx times g of x. And if I distribute on the left-hand side, then we have e to the integral p of x dx times y prime plus e integral p of x dx times p of x times y equals e integral p of x dx times g of x. I'd like you to try and recognize this piece right here. It's the interaction when you distribute this term over this addition. It's the interaction between the integrating factor and the p of x times y term that makes the special stuff happen. So this is just mu of x times y prime plus something interesting times y. What is this? This is mu of x times y primed plus, right, now I could just call this mu of x times p of x times y, but that's not what I'm going to do. I'm going to group the mu of x times p of x together and ask you to help me interpret it. Think chain rule.
The derivative of mu of x?
Hell yes, it is. Right? Did everybody hear what Maxwell just said? If you differentiate mu of x using the chain rule and the fundamental theorem of calculus, you realize that you want to differentiate e raised to some stuff. Well, of course, you're going to get e raised to that stuff back, but then you also need to multiply by the derivative of the inside. Well, what's the derivative of the integral of p of x dx? The derivative of the integral of p of x dx is just p of x by the fundamental theorem of calculus. So this piece right here is mu primed of x. So what you have here is mu of x times y prime plus mu primed of x times y equals this thing on the right hand side. It is what it is. We can't, there's not much we can really do with that. I'll just write it as mu of x times g of x. Not terribly interesting there. Don't really care on the right hand side all that much. It is what it is. Sorry, shift you spool. So yeah, the magic is recognizing that this piece right here, these kind of two pieces together form mu primed. And that's coming from the chain rule. All right, if you don't believe me, take your time, come off to the side, calculate the derivative of mu. It just follows from the chain rule. You get e to some stuff back, and then you multiply by the derivative of that stuff. Well, the derivative of that stuff is just p of x. This is by design. Okay, now what's the left-hand side? We've got mu times y prime plus mu prime times y. That's the derivative of mu of x times y. Or if you want, you could write it as d dx of mu of x times. So the equation becomes and again use the prime notation, mu of x times y all primed is equal to mu of x times g of x. And we can integrate on both sides. When you integrate on the left, the prime just goes away. You get mu of x times y equals integral mu of x g of x. And you could plug in the formula for mu e to the integral p of x dx and then try to solve this for y. But really the idea is here, now you've got just a y on the left multiplied by mu of x, so you can solve this for y. So after evaluating the integral, we can solve for y. That's it, that's the proof. In other words, what this does is it takes a general first order linear equation, turns it into a separable equation. This is actually a separable differential equation. The notation isn't as nice as you're used to seeing them, because it's not just like dy dx, but if you make a substitution, you call some new function like v mu of x times y, then this would be dv dx equals, again, some new notation, call this function w. You get dv dx equals w, and you just multiply both sides by dx and integrate. So that's it. That's how these work. There's some notation, sorry, not notation, some terminology that I want to share with you. And then we're going to do some examples. It's kind of two new words I'm going to teach you today. First, any questions on the proof? Any questions on kind of why this works? It's always good to explore that. Okay. Terminology. Two new words. First, transient solution. Transient solution is a piece of the solution, or the whole solution itself, maybe, that goes to 0 as x goes to infinity. So G, for example, if y equals e to the negative x, called c1 e to the negative x plus c2 x squared is the solution to an ODE, we'd say the C1 e to the negative x piece. It's transient because as x goes to infinity, x 0. Right, so we've seen the kind of multi-parameter families of solutions for ODEs in the past. We're going to see more of them showing up in the future. If your solution has a couple of pieces, and one of those pieces goes to 0 as x goes to infinity, we call that piece the transient solution. We'll see in the future that you can have many kind of pieces of your solution. And sometimes one of them is in a sense stronger than the other as x gets larger and larger. I'm going to show you a real concrete example here. I'm going to make sense of it using direction fields, but just the terminology. What is the transient solution? It's the solution that goes to 0 as x gets larger and larger. Transient often meaning like comes and goes, right? Like people talk about the transient nature of Gainesville because people come here, they stay for a few years, and then they leave. This guy shows up in the solution of the differential equation. He hangs around. If x is close to 0, he's reasonably important. But as x gets bigger and bigger, he becomes less and less important. He goes away after a while. So we call him transient. The other bit of terminology singular point. We say that the x value x naught, the input x sub 0 or x naught, NAUGHT naught for 0, is called a singular point of the first order linear equation y prime plus p of xy equals g of x. If this guy, p of x, is undefined or discontinuous, let me say poorly behaved. As x goes to x naught. This can happen in lots of ways. Maybe p of x blows up to infinity or to negative infinity as x goes towards x naught. Or maybe p of x has some sort of like jump discontinuity. Usually what you'll see there is what's called a pole, like blowing up to infinity. But if the function p of x is badly behaved, discontinuous, and whatever flavor you want, as x approaches x naught, we'll call that a singular point. Practice that, could be massively rapid oscillation. That would also give me something like this. And the differential equations that come from real world situations, it's almost always a blows up to infinity thing. The term singularity is one of those terms in mathematics that's hugely overused. But yeah, that's all. Okay, singular points, these are going to be really important when we talk about series solutions to differential equations. And the concept of a transient solution is going to be one of those things that's useful if you're interested in numerical solutions to differential equations. Both of these bits of terminology will show up in your homework. Okay. And a quick example of a singular point. Let's look at the ODE. First note, this is not in standard form. First order linear equation, but it's not in standard form yet. 0 divided by x squared is 0. So to get that into standard form, I had to divide through by the thing multiplying y prime. I had to multiply or divide through everywhere by x squared. So p of x is cos x over x squared, which is poorly behaved as x goes to 0. So we'd say x equals 0 is a singular point. So singular points you can recognize pretty early on. Transient solutions, you need to solve the differential equation before you can recognize them, because of course there are solutions. So that's enough talk. Let's go ahead and solve an equation. Inseparable. Let's not do this. Well, no, let's not do this. So I guess comment here on one of the book's examples. Many of the equations that we've seen already, many separable equations, could be solved this way also. In fact, any separable equation could be solved using integrating factors, but it's unnecessary. So word to the wise, if you're just given a linear first order equation, you should always check if it's separable first. One last bit of talk, sorry. All right. Always check if it's separable first. If it's separable, just separate variables and solve that way, because it's faster. Okay. Whew. Right. So what would be fun? Let's find one that's fun. One that we played with the other day that I think I could use here. Oh, we'll use this example. We'll start easy. We'll start easy. Okay, here we go. Oops. So here's a first order linear ODE. Is it in standard form?
No.
No, it's not. So if I want to use integrating factors to solve this, I need to first write it in standard form. Now, before I do that, per the note above, I should check if it's separable. Is this separable? How would I check? Well, I try to separate variables, right? Remember, a separable equation is one where you can write it as y prime equals some function of x times some function of y. So let's solve this for y prime. What would I get there? I'd have x to the 6 e to the x plus 4y all divided by x. And the question is, can we write this as like h of x times g of y? Can I split that up as a product of two functions, one that is just x stuff and the other that is just y stuff?
No, you can't.
Yeah, I don't think so, right? I can split this up as x to the 5 e to the x plus 4y times 1 over x. But I can't like factor out a y. There's no way to split this as a pure function of x times a pure function of y. So this is not separable. Sometimes you got to look pretty hard. Sometimes the algebra tricks to separate the variables are not obvious. But no, this one is not separable. So, okay, is it in standard form? So now that it's not separable, we know we're going to use the method of integrating factors. So I got to put it in standard form. Are any of these things here standard form?
No, they're not.
No. So let's take this original expression and try to put it into standard form. I'll just rewrite it here. Let's see where we're working from. Remember, standard form should just have y prime plus some function of x times y equals some shit just involving x's. So on my right-hand side, I only have x's. There's no y's over here that I need to pull over and group with this term. That's good. The problem is this guy. So I'm going to divide through everywhere by x, which is going to introduce a singular point. Or it'll help you see a singular point. Remember, when you do something, do it to both sides. For some reason, especially in this section, people tend to forget to divide or multiply on the right-hand side by the integrating factor or by whatever it is they're doing here. So when I divide both sides by x, this becomes 4 over x. This becomes x to the 5. Okay. What now? Is this now in standard form? Am I happy?
Yeah, no, you just need to find the integrating factor.
Yeah, very good. So this is standard form now. I've got y prime plus p of x y equals g of x. So just for fun, p of x here is negative 4 over x. And g of x is x to the 5 e to the x. So now, yep, find the integrating factor. New. That's going to be e raised to the integral of p of x dx, which is e raised to the integral of negative 4 over x dx. What's the integral of negative 4 over x?
Negative 4 ln of x.
Very good. Yeah, the negative 4 pops out. I'll do this kind of explicitly once. This is e raised to the negative 4 integral 1 over x dx. And the integral of 1 over x is the natural log. So this is e raised to the negative 4 times the ln of x. We don't write plus c's when we calculate the integrating factor. Fun fact. For mu, you can use e raised to the power of any antiderivative. So while we don't write a plus c here as a rule, we don't normally write a plus c. If you wanted to, if it somehow helped you to do so, you could write negative 4 ln x plus 5, or negative 4 ln x minus 4. You could include any particular plus c you wanted. But when we calculate the integrating factor, as a rule, we don't do any plus c's with this integral. We're just looking for e raised to some antiderivative. So this is a reasonable choice. I am assuming here that x is positive. If you wanted to avoid that, you could write absolute values, but we'll let that go. Now I multiply through by this. Multiply through by mu, and it has to be the version in standard form. Remember, that's a big deal. If I multiply through this by mu, nothing good happens. If I multiply through this by mu, good shit happens. So, sorry, one more thing. What is this equal to? Nobody would leave that written like this. This is
1 over x to the 4th.
Yeah, very good. We bring the 4 inside. This is e raised to the ln of x to the negative 4. Sorry, which is just x to the negative 4. 1 over x to the 4. Sorry about that. So when we calculated our integrating factor, we got this. Using rules for logarithms, you bring the negative 4 inside the ln. And then e raised to the ln of some shit is just that shit. So this integrating factor, mu of x, is really just 1 over x to the 4. So I'm going to multiply through by this. I get 1 over x to the 4 y prime minus 1 over x to the 4 times 4 over x times y equals 1 over x to the 4 times x to the 5 e to the x. And we can combine terms here, we can combine terms here. Building 1 over x to the 4 times y prime minus 4 over x to the 5 times y equals 1 over x to the 4 times x to the 5 is just x. And now the trick is to interpret the left-hand side as a derivative, product rule derivative. Remember what we said in our proof, the left-hand side should always be the derivative of mu times y. And mu here is 1 over x to the 4, x to the negative 4. And it is. This is mu times y prime plus mu prime times y. So I'm going to help you see that. So this left-hand side here, I claim that this really is this, and that it's just a product rule thing. Well, I'll just check, I'll show you here. I'm just gonna do this on this one problem. I wouldn't write this out. I differentiate the y, I leave the x to the -4 alone. And then I'm going to leave the y alone, but differentiate the x to the -4. I got -4 x to the -5 y. And that really is 1 over x to the 4 y prime minus 4 over x to the 5 y. That's 4. And that's my left-hand side, right? That's what we got. So let me call this equation star. Call this equation 2 star. That which is the LHS 1 star. So my original differential equation, this thing, is equivalent to 2 star, this thing. And now if you integrate on both sides, we get, on the left-hand side, when you integrate this apparatus, the prime goes away, right? You integrate a derivative, you get the original function back. And on the right-hand side, you have the integral of x e to the x dx. Okay. Any questions here? We all comfortable up to this step? Okay. So my original differential equation equivalent to this integral equation. In order to solve the problem now, I just need to evaluate this integral and then multiply both sides by x to the 4 to get y alone. So my goal is just to find y. How do we integrate x e to the x?
Integration by parts.
Very good, thank you. That's Ross. Yeah, we do some IBP. U here is going to be x. dv is going to be e to the x dx. du is just 1 dx. And v is e to the x. So you get 1 over x to the 4 times y is equal to u times v, x e to the x, minus the integral of v du. And here I will go ahead and write a plus c, right? At this step, this last integral, we do go ahead and write our plus c here. So we got 1 over x to the 4 times y is equal to x e to the x minus e to the x. And you could write a plus c or a minus c. A plus c, because additive constant. Same thing as subtracting it because it's arbitrary. Constant could be anything. So now we're almost done. My very last move here is just to solve this equation for y. So I get y equals, and multiply both sides by x to the 4. So this will be x to the 5th e to the x minus x to the 4 e to the x plus c x to the 4. And that's your solution. That's it, you're done. So first order linear equations, not too bad. If you're lucky, they're separable. Solve them by separating variables. If you're slightly less lucky, then you use this integrating factor trick. It's a great trick. Generally, you'll have to do 2 integrals. If you're using the integrating factor thing, you have to use 1 integral to calculate the integrating factor, and then a second integral at the end. And these problems are exactly as hard as those integrals. Sometimes those integrals are trivial. Sometimes those integrals require a little bit of a trick. Sometimes those integrals are impossible. I advise you to, practice, stretch your calculus legs a little bit. So that's good. It's good to do. Questions on this particular example? Okay, let's look at another one. So this time I'm going to kind of slow down and explain less than I did last time. That last one we kind of really took our time. Here, I'll show you how I'd solve one of these. Let's do an initial value problem. Let's do one like last time, didn't we look at you guys remember this? We looked at the direction field for this, this differential equation the other day. Here I'm going to think of it as an IVP subject to the initial condition that y of 0 is equal to 4. So we were able to look at some solution curves last time. I don't have that open anymore. We're able to look at some solution curves to this by drawing the direction field and then plopping our initial conditions where we wanted within that. But we don't know what that solution actually was. We weren't able to find that solution analytically because this is not a separable equation. So quick check, separable. No. Standard form. Not yet, but we'll get it there. So again, I'm going to rewrite this as like y primed x plus y, and that's equivalent to saying y primed minus y equals x. So there's your standard form. The integrating factor then, mu of x, e raised to the integral of p of x dx. So p of x here is the constant function -1, and the driver input is the function x. Well, my mu is e to the integral p of x. That's e to the integral of -1 dx. P of x is -1. And the integral of -1 is just -x. So my integrating factor here is just e to the -x. And then I'm going to take this equation in standard form and multiply through by mu. I'm writing the x first on the right-hand side just because it looks nicer like that. And this left-hand side, we can recognize as the derivative of e to the negative x times y. On the right-hand side is the right-hand side, hasn't changed. So integrate on both sides. When you integrate the prime on the left, you just get the thing inside. On the right-hand side, you've actually got to do the integral. This is again integration by parts. The IVP here is not bad. So you get that e to the negative x times my solution function y is equal to negative x e to the negative x minus the integral of negative e to the negative x dx. It's negative x e to the negative x plus integral e to the negative x dx. Just simplifying the minus signs. And then doing this integral, you get a third negative sign. So this goes back to being a minus negative x e to the negative x minus e to the negative x plus a constant. Questions so far? Okay, then I'll solve this equation for y by dividing both sides by e to the negative x or multiplying both sides by e to the x. Therefore, y is equal to e to the x times this whole thing. That is so if I distribute here, negative x e to the negative x times e to the x, that's just negative x. E to the x times negative e to the negative x is just minus 1. And then c times e to the x is plus c to the x. So that's it. Pretty quick, right? Not bad. Right? So you calculate your integrating factor, multiply through by the integrating factor, interpret the left-hand side using the product rule, integrate on both sides, do that integral on the right-hand side, however you must, sometimes IVP, sometimes trig sum, sometimes partial fractions, sometimes something else. But get that integral done, and then take the resulting equation, solve it for y. Clean up your solution as much as possible, please. Any questions on any of this? Okay, I want to see this in the context of what we were talking about last week. So I'm going to do two things here. Let's open up Desmos. And let's also take a look at and put it in your modules. Yeah, the direction field tool. This is nice. All right, so what did we do? We did 0, 4, right? We said we wanted a y of 0 to be equal to 4. Here's the curve it gives us. And let's see what we get if we graph our guy. Now, I haven't finished solving the IVP yet. I just noticed that we haven't specified C at this point. But depending on the value of C, you see we're getting solutions that look like this. One of those values of C is going to send me right through here. All right, maybe it's 5. Looks like it's 5. Neat, right? And again, you see the fact that all of these solutions kind of coalesce towards this line. That line is negative x minus 1. It's this part. And this guy, he's not transient because x doesn't go, this function doesn't go to 0 as x goes to infinity. But as x goes to negative infinity, this piece does go to 0. And that's why you're seeing all of those curves kind of getting closer and closer to this line as you run off to the left. So if we want to go ahead and finish this up. Finally, to meet the initial conditions, y evaluated at 0 should be equal to 4. And what we require 4 is equal to what you get when you plug 0 in over here. So it'd be 0 minus 1 plus c times e to the 0. It's the same as saying 4 equals negative 1 plus c. Plus our solution, y equals negative x minus 1, 5 e to the x. Not so bad, right? Okay, so the problems I put in your homework set using these things, they're not especially hard to understand. I don't think you'll have a terrible time with them. And hopefully, you start to develop a little bit of confidence understanding how to solve differential equations, or at least some of these nicer differential equations, these first order linear equations. Linear equations are awesome. They're a huge deal. And the first order equations we can actually solve all of. We're going to talk about other linear equations down the road. Turns out constant coefficient linear equations pretty easy to manage, but shit gets out of hand fast after that. I want to introduce one other kind of family of differential equations today before we go. And those are the so-called exact equations. So before I move away from this, any questions on integrating factors or first order equations, first order linear equations? And, let me see, how much time do I have left? Getting close. All your time. 11:20. Yeah, we're good. All right. So we're going to introduce section 2.4, and then we're going to talk about the test. if z is a function of x and y, then the differential dz is defined to be dz equals, I really like the subscript notation here, but your book doesn't use it, so I won't use it. It's defined to be the partial derivative of f taken with respect to x times dx plus the partial derivative of f taken with respect to y times dy. If you're taking Calc 3, then you've seen this concept before. If you think about the level curves for a function like this, and the notion of a level curve is like if I set this equal to a constant. How do I explain this for those who haven't had Calc 3? Let me see if I can find some good pictures. Here we go. Level curve. These are more complicated than they need to be. Here we go. All right. Where's my picture? Here. So if the graph of a function like this, the graph of a function of two variables is a surface, right? It's like a picture like a topographical map, right? It's like mountains and valleys and shit. The input space is down here. It's two-dimensional. It's the XY plane. Those are all your inputs. And over any point in the plane, there is a specified height. That's your z. So the graph of a function of many variables looks like this. A level curve is what you get if you set that function equal to a constant. So I'm looking at all of the curves in the XY plane where the z value, the output from that function, is the same. So again, on a topographical map, on a topographical map, kind of you see those lines where the altitude is the same, those are level curves. Or here, these black lines, these are called level curves. So if you look at the level curves for a function like this, then you can look at the external derivative or the differential of that function and say along that level curve, it would have to be 0. Because if I set this equal to a constant and then I take differentials, then the derivative of the constant is 0. So you'd have this expression equals 0. Some differential equations look like this. So the idea is some differential equations can be thought of as dz equals 0 for some function of z equals f of xy. These are called exact equations. And then the trick is, if you know that you can interpret an expression like this as, you can interpret a differential equation where you've just got some bullshit here times dx plus some other bullshit here times dy equals 0. If you know you can interpret that as the differential dz equaling 0 along some level curve for some particular function f, there are nice ways to solve the differential equation, right? That's the idea. But we need to know what type of differential equations, when do we see an expression like that, and are we free to interpret it in this way? there's a particular condition. So I'll go ahead and share that with you, and then I'll show you how to look at it. Okay, so there's some more notation here. We saw in the first homework set that you can write differential equations in that differential form, where you've got like something times dx plus something times dy equals something else. Well, right. So an equation of the form an equation of this form is said to be an exact differential equation if the left-hand side can be interpreted as the differential of some function, right? The exact differential of some function. Is the differential of, is the differential of some function. But how do you know if that's the case? How do you know if the thing you're looking at could possibly be the differential of some function? It turns out there's a specific criterion, and this is closely related to the concept of a harmonic conjugate in complex analysis. Turns out this is the case. And it might be an if and only if. Yeah, it is. If and only if the partial of this function taken with respect to y is equal to the partial of this function taken with respect to x. And this may remind you of the Cauchy-Riemann equations from complex variable theory, if you've heard of that. Sorry, excuse me. So if you're given a differential equation, a first order equation, and you want to know if it is an exact equation, this is the thing you need to check. You check this. And then the way you solve is kind of by integrating each one of those functions with respect to the appropriate variable and adding on a function of the other variable. We don't need to run through the proof, but I would like to show you a solution, right? So how am I doing on time? Do we have time to actually go through this? Maybe we should just check if one or two are exact. Let's check if a few equations here are exact or not. Where's a nice example one? So you got to hold on to this, right? This is the big thing for section 2.4 is you get an equation that looks like this. You want to know if it's exact. I'm going to show you a new method of solution. But before you can apply that method, you have to check whether this condition holds. So let's check if the differential equation, let's do x squared y cubed dx plus x cubed y squared dy equals 0 is an exact equation. I want to point out that we could write this differential equation a bunch of different ways. Right? I could write this as dy dx equals y over x. Right? This is actually equivalent to the differential equation dy dx equals y over x, or negative y over x. We want to know, though, is this an exact equation? So I have to identify the functions m and n. M of xy is all the shit multiplying dx. This is m. It's m of xy if you want. And this is n. Another kind of quick remark, the notation, if you want to, you can write this as m sub y equals n sub x in the subscript notation. Remember, that's the alternate notation for partial derivatives that I really prefer because it's much nicer. But for this example, at least I'll go ahead and write it out in the full curly Leibniz notation. So what we want to check is that the partial derivative of m taken with respect to y is equal to the partial derivative of n taken with respect to x. It's a good opportunity for us to see if we remember how to take partial derivatives. So we're taking the curly d dy derivative of x squared y cubed. What is this derivative?
3x squared y squared.
Excellent. Remember, we treat the x squared as a constant. So really, this is just like differentiating 5 squared times y cubed. So we're really just differentiating the y cubed. The x squared comes along for the ride. This piece has derivative 3y squared. So this would be 3x squared y squared, writing the 3 out front. I want dn dx. That comes from applying the curly ddx operator to x cubed y squared. And again, treating y squared as a constant, it's just a constant multiple. We're really only differentiating this piece. We get 3x squared y squared, which is the same thing. So since these do match, the differential equation is what we would call an exact equation. In the future, I'll use the subscript notation here because I'm lazy. Y and x. Okay. So how do you solve these? What does it even mean to solve these? What are we trying to find? Kind of my goal here is to find the function f whose total derivative or differential is being taken. And the idea is I sort of know the first partial derivative with respect to each variable. So if I know that my equation is exact, I'll bring you back here. So do I have the other side here? Then df dx is m, and df dy is n. So if I were to integrate this piece with respect to x and integrate this piece with respect to y, I should recover something like my function. So sort of important stuff here. Make sure that your notes are clear. And the big idea is that if this condition is satisfied, then I can really trust that this is df dy. Or sorry, df dx. And that the other guy really is df dy. We got plenty of time. Let's go ahead and take a look. Big idea. If mxy dx plus mxy dy equals 0, then mxy is dx and xy is dy. Sorry, is exact. So if your differential equation is exact, then each of these sort of coefficient functions here are the first partial derivative of your solution function with respect to one or the other variables. So I should be able to recover the function f by integrating this with respect to x and by integrating this with respect to y, doing kind of a partial integral, really just integrating with respect to the one variable. The catch is when you do that, rather than having an additive constant, what you actually have is a constant, a function of the other variable in place of your additive constant. That's the only way to say this. So how do we solve these? We integrate. Hence, we can solve exact differential equations by integrating. Since df dx is equal to m, we see that f should be equal to the integral of m done with respect to x. And normally when you're working with a function of a single variable and integrating with respect to that single variable, you would get a plus c. But here I'm working with a function of several variables, but I'm integrating with respect to just one of them. So instead of a plus c, what is a constant with respect to this differential operator, the partial d partial x operator? A constant is any function of y. And this is symmetric in the variables. Oh, your book uses a G here, not an H. Sorry, I'll use a G. Doesn't matter. And the process is symmetric in X and Y. So you could go the other way also. So again, this is kind of replacing your constant of integration because your function is a function of both x and y, but you're integrating just with respect to x to try and undo this partial derivative. This integral is not hard generally, but you need to be able to find this function. So after you do that, you're going to roll through this with your dy derivative and then set the whole thing equal to your n function. So now we have a guess at what f is. Then we use the fact that df dy is equal to n of xy to try and find this function g. So what we'll do is we'll say, okay, this should be d dy of all this shit, because that's supposed to be f. So this should be equal to n. And that'll give you something you can solve. You'll take the regular derivative here, you'll take the partial derivative here, and then you'll have an integral equation. You'll have like g primed of y equals some stuff, and you'll try to evaluate that. So this yields g prime of y equals n of xy minus the derivative here. And that's it. You had a function that you suspected was f. The only thing you needed to do is identify this guy. And then the way you identify this guy is by using the other condition, the condition that df dy is n. So since df dy is n, you can take d dy of this, because this is f, and set that equal to n. That lets you solve for g prime. And then you can recover g from that. So it looks messy, it looks complicated, but this is the big idea. And it's one of those things where surprisingly you can kind of follow your nose. So let's do it. Let's go ahead and solve one. I think we have time. Yeah, we got 6 minutes. 6 minutes we can solve one. Here we go. So we're going to solve the equation 2xy dx plus x squared minus 1 dy equals 0. So here m is this guy and n is this guy. I should check that the partial derivatives match in the way they're supposed to. Dm dy is equal to dn dx. So, well, exact. Well, my, if I differentiate this guy with respect to y, hey, relax. Sorry, guys, I have somebody at my door. Give me one moment. Somebody's trying to sell me tree trimming bullshit. All right. Check if this is exact. We need to check if my or dm dy is equal to nx. That's the question. Well, my, or dm dy, is the partial derivative of this taken with respect to y, so that would just be 2x. And nx, if I take the partial derivative of this with respect to x, I get 2x minus 0, which is also 2x. So yep, this is exact. So the idea, big idea then, is that I can recover my function by integrating each of m and n with respect to the appropriate variable. So in particular, the way we're going to do this is hence df dx is equal to m, and df dy is equal to n for some function f. My goal is to find that function f. So I'm going to take this guy and I'm going to integrate with respect to x to try and undo that derivative. That's the big idea. So since df dx is equal to m, which is 2xy, we can integrate on both sides to see that f of xy is equal to the integral of 2xy done with respect to x plus some pure function of y. This makes sense. You've got the derivative of your function is equal to 2xy, and that derivative is with respect to x. So if you integrate 2xy with respect to x, you should get your function back. The only catch is, since it's a function of multiple variables and you don't know what's going on with respect to y, you have to add on your pure function of y. If I do this integral, again, treating y as a constant here, the x would integrate to x squared over 2, which is just x squared. So here, pop out the y, pop out the 2y, and have an integral of just x dx plus g of y. It's kind of mechanically how we would think of it. And then that integral is not hard. So it's just going to give me, let's see, 2y times x squared over 2. So this is just y times x squared plus g of y. All right. Do we understand what's going on up to here?
Yes.
All right. So now we've gotten everything we can possibly get out of this condition. I know that I'm looking for a function f whose first partial with respect to x is 2xy. All of the functions like that are of this form. If I want to identify my particular function, I need to figure out this g. And the only way I can get any more information out of my differential equation is by using this condition. So therefore, since df dy is equal to n, which is x squared minus 1, we see that dy of yx squared plus g of y, this all should be equal to x squared minus 1. And if I go ahead and take that derivative, remember, don't be intimidated by the partial derivatives if you haven't seen them before. It just means treat everything else as a constant. So when I differentiate this piece with respect to y, treating x as a constant, I just get x squared, right? The y differentiates to 1. The x squared is a constant multiple. He just comes along for the ride. And then the derivative of a pure function of y, since there are no x's in there, I can say that this is just going to be the same as the regular derivative of y, g primed of y. And that has to be equal to x squared minus 1, because we know df dy is x squared minus 1. This, I now want to try and figure out the function g. Subtract x squared from both sides. And you see that g primed of y is just -1. And the kind of big thing here in this last step is to remember that g is a pure function of y. G doesn't have any x's in it at all. So now you can integrate on both sides to deduce that g of y is just -y. Because we know that the function g is a pure function of the variable y. Because it was coming like the constant of integration from a partial ddx derivative. Now we put all this shit together. I know that my function f is yx squared plus g of y, and I know that g of y is -y. Thus, f of xy is equal to yx squared plus g of y, which is yx squared minus y. Not too bad, right? Now remember, the last thing we need to look for here is the fact that the supposition that we made is that the exact differential equation came from looking at level curves. Of the function f. Meaning curves along which f of xy is equal to some constant c. Level curves come from fixed but arbitrary constants. So the solution to my differential equation is going to come from setting this function equal to a constant and then solving for y. And if possible, all right, if possible, solving for y. And in this case, we can. So here we have c equals yx squared minus y. Rewrite c equals y times squared minus 1. Right, that's y on the left, y equals c over squared minus 1. So this is the family of curves that solve the exact differential equation we began with. Really, the money is all in finding this function f. And then you just remember that your exact DE comes from level curves, looking at the differential along level curves. So once you find your function f, substitute and plug in c for f of xy, and then if you can, solve for y. I want to say again that this is the same thing as finding harmonic conjugates in complex analysis, which is a really cool thing. I think we're probably pretty close to being out of time. Oh, we are over time. So let me go ahead and run this poll. We've covered exact equations, solutions by substitution. I'll leave it up to you guys. Do you want the exam to be this Thursday and stopping at 2.4, or next Monday stopping at 2.5? Let me go ahead and cast the poll. Let's do it. Yes. And we'll make it anonymous. So I'm going to go ahead and launch the poll. Your choice. The exam is either this Thursday and stops at 2.4, or next Monday and includes one more section. Either one's fine with me. Still waiting on. I don't think it's going to wait for me to vote, so I do think I am still missing somebody. Oh, but the next Monday is ahead by enough that it doesn't matter how one person votes. All right, exam is next Monday and goes through section 2.5, which is a section we haven't lectured on yet. So I'm going to go ahead and show you guys a little bit more exact equations examples tomorrow, and then we'll start talking about substitution. The substitution section is a little tricky, no lie, a little tricky, but we'll get through it. It'll be okay, and then that will be the cutoff for the exam 1 material. That means I'll publish your study guide tomorrow after we go over the 2.5 stuff. And that's it. That's the plan. All right. So I'm going to go ahead and make the changes in the Canvas calendar. You'll see that reflected. Watch for the study guide to drop on WebAssign. There's also going to be a new homework set coming. If you have any questions, you can come see me in office hours. Otherwise, send me an email, Canvas message. I'll be happy to help you as much as I can. Have a good day, guys. Oh, I see there's something in chat. Yeah. Oh, yeah. You have a good day, Charles. Thanks.